Come here, boy. Ah! Huh? Ah! For Sparta! Ah! Oh man, I hope they're alright. Oh, they are. How do you know? Allow me to show you. No, that's not it. Not that either. I'll save this for later. Did bread just come out of your briefcase? Nope. Ah! How are these things coming out of your briefcase? Aha. Here it is. What is it? It's my time machine. That's not possible. Ah, but indeed it is. Here, let me show you. Ah! Whoa! Hello again. We've traveled back in time. Come here, join me. Okay. Now that we're here before the crash occurred, allow me to explain something to you. You probably are wondering where on the road these two cars crashed. Well, not really, but... Well, you see, in this situation, the motorcycle is going 25 meters per second to the right, and the man in the Spartan costume on the horse is going 15 meters per second to the left. And we know that the road is 200 meters in length, with each vehicle on either side of the road. If these two vehicles meet at the same spot, we can deduct that the distance the motorcycle will travel plus the distance traveled by the horse should equal to the total distance between them. Think of it this way. Remember that dog from earlier? The dog and the boy were the same distance apart from each other, and they met at one spot, right? But for this situation, it's easier to tell where the two will meet since only the dog is moving. Say the dog originally was moving at 8 meters per second, but now the boy and the dog are moving at half the dog's original speed. The distance between them doesn't change. Now to the next part. We can't immediately figure out where they will meet just yet. The specific math model for this situation would be velocity of object times period of time equals distance between the starting point and meeting point. So far, all we know is the velocity of the two objects. However, what if we change the situation so that, just like the dog and the human, one object carries the velocity of both objects combined? The distance between both objects doesn't change. So, for the motorcycle and the horse, their combined velocity, ignoring direction, would be 40 meters per second. Delta distance divided by delta velocity equals time, so 200 meters divided by 40 meters per second equals 5 seconds. Now that we have the period of time it would take for the two vehicles to crash when traveling 200 meters, let's separate the velocities again and apply this period of time to our original specific math model. 25 meters per second divided by 5 seconds equals 125 meters. So, from the perspective of the motorcycle, the two vehicles would meet at 125 meters. That had literally nothing to do with my original statement.